what's going on today? Well, the plan is to now replace CosmoQuest Astro office hours with essentially a discussion between me and Joe that will allow us to explore the universe. And we're asking you guys to come along on this ride with us. And so today's topic of discussion will be our very own planet Earth. And so, really quick caveat here for these streams. No question's a dumb question. If you guys have questions, ask away. Some of the questions I'll be able to answer, or Joel will be able to answer. Some of the questions I may not be able to answer. But we'll find out what the answer is and get it to you. Whole point here is to learn. Alright, with that stated, let's go ahead and dive into today's topic, planet Earth. So, as you can see here, a nice little beautiful picture in the background of our Earth as it is, or what it looks like today. However, it didn't always look like this. So let's go ahead and go back into time to get an idea of what planet Earth was at the very beginning. And to do so, we have to go back to when our solar system was actually initially forming. And so what we're seeing here, we all know it's flat. Yes, it is. It's flat.
Class is over. The Earth's flat.
Yeah, class is over. The Earth's flat. That's what Joe just stated. But Earth's formation, it all began many billions of years ago. And what happened was there was a cloud of molecular gas and dust, an extremely big cloud of this material. And so our particular portion of that big cloud of molecular gas and dust was about a clump of the size of 1 parsec in radius. And so what happens is we have this essentially ball of gas and dust, and it begins to coalesce, which basically means it begins to come together, and it's coming together based off of its own self-gravity, pulling all of that material together. Now, in this particular image I'm showing here on the right-hand side of the screen, it's an image taken by NASA's Hubble Space Telescope of the Ring Nebula. Now, the initial larger ball of gas and dust was much bigger than this. But this is a good example of a nebula, which is a perfect place for star birth. So, with that particular clump of 1 parsec radius of gas and dust, it began to collapse more and more. However, as it began to collapse, it began to also spin up faster and faster. And because it's spinning up faster and faster, it's also beginning to undergo along its outer portions, begin to flatten as well. And so, all of this is tied into conservation of angular momentum. And the idea you can kind of get here is, if you've ever seen a figure skater, and they go into one of their twirls, if their hands are stretched out, their twirls will be extremely slow. But as you begin to pull their hands in closer and closer, or as their mass begins to kind of come closer and closer together, they begin to spin up. And it's pretty much the exact same thing going on with this ball of gas and dust. Except now the outskirts of the ball are flattening out. And so eventually, at some point, at the very center of this ball of gas and dust, you're going to have the material that's going to be used to make your star. Or in this case, our sun. However, for that disk, you can use that disk to make other things. For example, like asteroids, moons, and the planets that host them. And again, nice pretty picture of a depiction of what our solar system looked like so many billions of years ago, thanks to an animator at NASA. Unfortunately, you guys cannot hear Joe right now. I'm pretty sure he's typing away probably in the background, so...
But yeah, no, I'm not doing much talking. I don't know if you can hear me any better. I moved my mic closer to my face per Pamela telling me to shout.
Okay, I can hear Joe. So if Joe asks any questions to me directly, I will let you guys know what the questions are, and I'm pretty sure Joe's probably just going to type some stuff as well. All right, so getting back to the Earth's formation. And I also need to make sure that I keep up with comments that are coming through. So how does gravity act on gases? Well, gases are a form of matter. Um, and basically, what's happening is the fact that they have mass to them. And so gravity is essentially the attraction between two masses. And because is made up of matter and matter has mass, each individual component of mass will attract another individual component of mass within the gas, causing them to come together. And so, what I'm showing here in this particular slide is an image of what we believe or what we think our solar system looks like today. Pretty accurate image. However, again, we're not going to talk too much about what's all going on in this image. We're not going to focus our attention even more so on, as I've stated here, the third rock from the sun, which corresponds to our Earth. So going from left to right, you have the sun at the far left, and if you just count 3 objects away, or 3 rings away, that particular ring or orbit around the sun would correspond to Earth's orbit, and you'd find a nice little pretty picture of a ball, a blue ball, a little small blue ball with another like natural satellite by it, which corresponds to our Earth. But as I stated earlier, Earth looks very different today than what it did many, many years ago. However, the internal structure for the most part has been the same, or the structure in general has been the same. So, what we're looking at here is kind of a breakdown of what our Earth looks like from the inside out. I heard Joe breathe. Did you have a question there, Joe?
Nah, I'm just getting frustrated with my t-shirt. The sleeves keep rolling up on me. I am not Fonzarelli. I don't need that,
man. Joe is having some clothing malfunctions right now. So what we're looking at here is an image of what our Earth looks like from the inside out. And so starting at the very center, we have a solid inner core. Moving out from that, a liquid outer core, which together makes the core of our Earth. Moving out beyond that, we have the mantle, and then we finally have the crust. Now, I've heard explanations of how we should imagine our Earth, essentially for the crust, and I think I've heard like, if you have an apple, the skin of the apple would kind of correspond to the thickness of our crust relative to Earth, the entire structure of Earth, which is actually quite interesting. We live on a very thin piece of solid material. But how did our Earth actually get like this? Well, as I was stating earlier, we have our sun in the center, and around our sun initially, we have this disk of material. And so, in the case of our Earth and also many other planets in our solar system, they rotate around our sun, and as they basically rotate around our sun, or as this material, rotates around our sun, it begins to clump together, and it's clumping together, of course, due to gravity. However, as you begin to form bigger and bigger clumps within a particular orbit around the sun, it's able to now better gravitationally attract other pieces of material that are within the same orbit. And so, due to this gravitational attraction, the materials begin to move together. Now, this motion also builds up kinetic energy for, let's say, for example, the smaller piece of material. So it's moving faster and faster, and eventually, boom, it collides with the bigger piece of material, and they kind of stick together. Now, this transformation of essentially gravitational potential energy on the smaller piece of rock into kinetic energy, and then once they collide, all that kinetic energy, or a great deal of it, is now transferred or transformed, excuse me, into heat from the collision. And so this is actually a nice heating mechanism for, or yeah, a nice heating mechanism that kind of goes into why the center of our Earth, or part of the center of our Earth, is liquid. The other reason, of course, is going to be due to radioactive decay. And so, as we now have essentially this liquid core of material at the center of our Earth, all the heavier stuff, which in this case would kind of correspond to iron and nickel, can now begin to kind of sink through that liquid material towards the center and make up the solid inner core of our Earth. And so that's exactly how we're able to get this kind of differentiation between within the inner portions of our Earth. I'm trying to quickly stop for a moment to also keep up with what's going on in the chat. So in the case of a star, which we will be having a greater discussion on in a future stream, you have a lot more mass, which means that the gravitational attraction is going to be a lot larger. And so it's in that situation, what keeps it together, essentially, a big clump of gas, is gravity. However, there's another force that's fighting to stop the star from collapsing in on itself. And again, we're going to save this for another stream, but to answer your question there, Hanny, the reason why the gas is able to come together for a star is because it's a lot more massive. Larry, to be very honest, I do not know the answer to that question. But it's something that we can definitely look up and see what the answer is to that. And so from there, now that we've talked about the structure of Earth, we can now begin to talk more about, well, exactly how old is the Earth? And so what we're looking at here is kind of a plot that kind of gets into explaining how we determine the age of the Earth. If you could imagine that you start off with, for example, some piece of material, and embedded within this material is a compound or a molecule. And what you know about this molecule is that it undergoes some particular type of nuclear decay. What you'd want to do, and I will explain what decay is in a minute, but basically what you'd want to do is you'd want to be able to measure for this piece of material how long it takes for it to go from its initial amount of material to decaying to a smaller amount of its material. And so what this plot is showing us is basically with the images within the plot, we're starting off with some initial amount of material, which we're just going to say it's equal to some a sub 0. However, over time, represented by the x-axis in the plot, we're kind of noticing that the amount of material that we initially started off with is reducing itself. And this particular plot is actually looking at how it's reducing itself by half of its amount. And what we kind of see is that it does so in equal amounts of time. Well, if you're able to determine a relationship for this type of decay, which we have been able to, and this plot is a good representation of the decay of a particular radioactive isotope, we can be able to kind of gain information as to how old that piece of material was that underwent this decay of material that was within it. And so To kind of better explain what we're looking at in this plot, though, along the x-axis, this would represent like a time axis, where every single factor of t, for example, 1t, 2t, 3t, 4t, and so forth, corresponds to one half-life, or a half-life of the substance, which is basically how much time it takes for the initial substance, so it starts off with amount A, sub 0, how much it takes for it to decay or lose half of its material to be, for example, half of its material. Um, this particular example, though, shows along the y-axis that this is for atoms of C14, which is actually a naturally occurring radioactive material that's in our atmosphere due to cosmic ray collisions with not neutrons, but um, nitrogen within our atmosphere. Excuse me. So I'm taking a quick moment to look at the comments here, and if I miss anything, Joe, let me know. I don't want to lose myself in talking. And so, who did Earth? Who did Earth date? That's funny. Um, and so, it's a key thing that we need to be able to take into consideration here when dealing with trying to get the ages of things. In particular, if you've grabbed, for example, you went into Earth, you've grabbed a piece of material. And the thing about it, the deeper you dig into Earth, the more access you have to things that were on Earth many, many, many years ago. But let's say that you've grabbed one of these materials and you want to be able to, for example, a fossil, and you want to be able to determine its age. Well, you need to know exactly what sort of radioactive isotope to examine. And the reason being is because different radioactive isotopes have different half-lives, which means that it takes a different amount of time for it to reduce by half of its initial amount. And here what I'm kind of showing is a bunch of different radioactive isotopes that have been determined where their half-lives, or the amount of time it takes for half of that substance to reduce itself um, to a half of its leftover substance, um, where we're kind of seeing that if we want to be able to determine the Earth's
Matt, your audio just went all the way out.
It went all the way out. That's not good. You guys hear me? Am I back?
All right, now you're back.
I'm back. All right. My apologies there for the audio drop out there. But basically, what I was saying was that if you want to be able to determine the Earth's age, which we know though is on the order of billions of years old, being able to use radioactive isotopes like polonium, bismuth, or sodium, or actually many of these, would do no good, because if they were in the material many, many, many billions ago, many, many billions of years ago, they wouldn't be there today, because all the material would have been already decayed to concentrations that probably wouldn't be detectable. However, a radioactive isotope such as like uranium would be able to last on the order of billions of years. So that would make a very good isotope to study as far as being able to determine the ages of materials that you may have grabbed from out of the Earth. Earth is with the moon. And so there's some other considerations as well, though. So to be able to actually kind of get a guess at what the age of the Earth is, you need to also know exactly, well, when the material was around many, many years ago, what was the initial amount of the radioactive isotope? To kind of understand that, though, or to kind of get an estimate of that particular value, in this case, that would correspond to that a sub 0 value that I was showing earlier in the plot. You need to understand the decay chains. You need to understand exactly, well, how does particular radioactive isotopes decay? And so to kind of explain what I mean by that is, there's three different types of nuclear decay. There's alpha radiation, alpha particle radiation, beta particle radiation, and then there's gamma radiation. And so essentially with the alpha particle radiation, what happens is you have an unstable isotope of some material or some element, and it essentially breaks apart. And the way in which it breaks apart is that it'll create some other isotope of some other type of element with one part of the break, and with the other part of the break apart, for lack of better words, you get an alpha particle, which is basically the nucleus of a helium atom. That's one particular type of radioactive decay. The other one would be beta decay. In this particular decay, you're losing electrons. And then with the last type of decay, which doesn't actually change the element itself, is gamma radiation, which is basically the emission of light from the isotope. All right, and so, and the very last thing, of course, is that if you can start to determine ages of the Earth itself, or estimates of the age of the Earth, given that we also believe that other types of objects in our solar system kind of formed around the same time, you're actually now also getting age estimates of other objects in our solar system. Specifically, more so for like the sun, because if you're in the camp that the sun was created before Earth, then that would mean that the sun, at the very least, is as old as the Earth. And so we now can move along to start talking about Earth's plate tectonics. And so, I mean, me myself, I've never been in a situation like this where the ground just started moving beneath me, but I'm pretty sure some of you probably have. But the reason why these quakes, or in this case earthquakes, occur is due to plate tectonics. And so what I'm kind of showing here is a map of our Earth, but it doesn't look like the typical map that we see. What we're kind of looking at here is actually these plates. So each of the divided regions corresponds to a single big plate. And every now and then, these plates move. But why is that? Why do these plates move? Well, to kind of get a better understanding exactly as to why the plates move, let's go ahead and look at this one particular image that I have here that kind of shows a breakdown of what the interior of our Earth looks like, top down. And so I'm actually going to start at the center of our Earth, or no, I'll start at the top, where if we look along the right edge of our image here, we kind of see some words here. So we have the lithosphere, which is a combination of the crust in the uppermost solid portion of the mantle. Then we have the mantle, which I'm going to come back to in a minute. And then we have our core, which is actually, as stated earlier, is composed of a liquid component and a solid component. Now, the mantle itself isn't exactly all the way solid. And the reason why it's not all the way solid is due to radioactive decays that are occurring within the interior of our Earth. Really, we should think of it more like, I don't want to say jello, but maybe like plastic. Because, of course, you can actually deform plastic. It's not extremely easy to deform plastic, but if you work hard enough at it, you can deform plastic. And so the idea here is that there's portions of the mantle of very large portion of the mantle.
We lost your audio again, Matt.
Oh no. Is the audio back?
It sounds like you slap your computer and then the audio goes completely dead.
That is crazy. Let's see, well, you can still hear me though. Joe? Hello? Joe? Can you guys still hear me? Hey Joe, can you hear me?
Yeah, you're back.
Okay, I'm back. All right. Sorry guys for the audio fail there again. I can't explain the reason why it's happening. But if Joe is losing my audio, then that would indicate that there's an issue with the internet connection. And hopefully, what did I just do? I got rid of us. Let's bring us back. All right. Are things good now, guys?
Yeah, good on my end.
Okay. I'm just going to go ahead and continue then. And so what's happening with a portion of the mantle is that it's kind of like this plastic substance. It's not really plastic, of course, but think of it like plastic. And on top of that plastic, we have the lithosphere, which is fairly solid. And we basically have these big plates, though, of the lithosphere. And when the plastic beneath us makes motion, it also causes these big plates of lithosphere to also move as well. And it's that motion of those plates that cause earthquakes. Let's make sure that I'm not missing comments. And I'm happy to know that everyone can hear me again. There was a thump. I might have hit my laptop, and I'm gonna. If that was the case, I'm just gonna avoid doing that. But yeah, that's basically how the plate tectonics work. We have our lithosphere, which is basically crust and upper mantle, solid upper mantle, and its motions cause the earthquakes. But its motions are because of the fact that the mantle itself is kind of like this plastic material that has motions itself, which causes motions for the plates.
Hey, Matt, one of the viewers has a question for you that I don't have any idea what the answer would be.
So a dumb question: can we estimate when plastic things can move the lithosphere? That's a very good question, and to be very honest, I don't exactly know the answer, but this is my thoughts on it, though. We can measure when movements begin or when quakes start to happen, because the vibrations would start slow and then they'd get much more faster. Because if we could measure when if we could measure in advance when essentially when earthquakes are going to happen, we just basically say everyone move, get away, and we can avoid a lot of really dangerous situations where people can end up dying. But I don't think we can actually measure when when there's going to be shifts in the mantle. At least major shifts to the point where it'll cause earthquakes that could be dangerous to living things. Okay. So moving on. But then again, I could be wrong. If I'm wrong, someone just let us know. So we've talked now about plate tectonics, and we can move along to another topic of that's important when talking about Earth, and that's Earth's surface temperature. And so I have an equation here, which I'll explain in a second. But let's kind of think about how to calculate Earth's surface temperature. And so earlier, I stated that, of course, we have our sun and we have the Earth. It's essentially 3 orbits away. Well, the sun itself is creating its own light, and that light essentially can hit things and heat them up. And so the sun serves as a perfect source of energy and heat. And so as sunlight hits one side of our planet, it causes our planet to heat up. And so that's kind of a source of radiation input. And that particular source of radiation input, if any of you guys have ever seen a blackbody curve, which corresponds to the amount of light that an object emits as a function of frequency or wavelength. If you were to look at the blackbody curve for the sun, you notice that a lot of the light that it emits is within the visible portion of the electromagnetic spectrum. And so we have a lot of this light hitting half of our planet and heating up our planet. However, our planet itself also re-radiates out energy that it receives. And so it's kind of like you have to kind of find the balance of the amount of energy that the planet is receiving, in this case from the sun, which kind of peaks in the visible portion of the electromagnetic spectrum. But then you have this radiation output, but the radiation output peaks in and it states here long wavelengths, but in the infrared portion of the spectrum. And so by looking at these two, essentially the power of absorption from solar radiation and the power of emission, essentially, the power of the emission of heat or energy from the Earth, and making a calculation with these two quantities, you can be able to determine exactly what the temperature of our planet or any planet is actually, or at least get an estimate. And so this equation that I'm showing down here, where T sub P represents the surface temperature of the planet, it's going to be equal to the temperature of our sun times this factor of 1 minus a raised to the 1/4 power, where a is a factor known as the albedo, which is in this case a planet's ability to be able to reflect sunlight. It ranges from values of 0 to 1, where 1 would correspond to a perfect reflector, meaning it would reflect all of the sunlight, versus 0 corresponding to an object that has no reflective properties at all. And then this is going to be times the square root of a ratio between the solar radius divided by 2d, where d represents the distance between the sun to the planet itself. But the calculation is not that hard. And maybe we might present a problem in the future doing the calculation or something. Maybe. We'll see.
Hey, Matt, what is the A in the formula for again?
The A is for the albedo of the planet. The albedo is essentially a quantitative measure of how reflective the planet is, in this case of solar light.
That's where you were talking about the range from 0 to 1 inside
Yes.
of there, 1 minus that reflective capacity.
Exactly. So if we were to do an analysis of this, and you guys can't hear Joe, but me and Joe are talking right now. But basically, if you have a planet that's a perfect reflector, it'll have a value of 1. And if you notice, 1 minus 1 is equal to 0, and then 0 times anything else is 0, which means its surface temperature would be 0. Because it reflects all of the sunlight that hits it. And of course, you can have the other extreme, where it's not a perfect reflector. It doesn't reflect anything at all. And then basically it's going to be the solar temperature times whatever the square root of that ratio is. But yeah, it's fun to look at that and be able to determine exactly what the surface temperature of the planet is. But there's a lot more to this calculation that I'm not talking about here. There's also the fact that if the planet has an atmosphere, that kind of modifies what the surface temperature will be, and we'll kind of come back to that a little bit later. So the very next thing that we're going to move on to is talking about Earth's atmospheric structure. So of course, we've already talked about what's going on underground, but now we're going to talk about what's going on above ground. So pretty much everything above the surface of the Earth, until you reach outer space, of course, is our atmosphere. And it's actually fairly thin. As you can notice here, our atmosphere kind of extends up to it looks to be about 400 kilometers, maybe a little bit more. Well, about 400 kilometers. Whereas if you go deeper into the surface of the Earth, we're talking about on the order of thousands of kilometers. But basically, what we're seeing here in this image are the different layers of our atmosphere. Starting off with the lowest layer, the troposphere, which is typically the layer in which you'd see airplanes flying. Wedged between the troposphere and the stratosphere, you're going to have our ozone layer, which is basically composed of O3 molecules. Then moving along from the stratosphere, we have the mesosphere, then the thermosphere, and then the exosphere, which is the outermost sphere of our atmosphere, which is kind of what space shuttles are trying to achieve. But what's really interesting about this is if you look on the right hand side of this image, we have a plot. And essentially the plot is showing as a function of, which is weird, because along the y-axis it's showing the altitude, which is typically the independent variable. But what we're seeing here is along the y-axis, and it really isn't a function given the orientation of the plot, but along the y-axis we have altitude, and along the x-axis we have temperature. And so as you move away from the surface of the Earth, you kind of see that the temperature is dropping, is lowering. However, once you kind of get past what we would correspond as the ozone layer, which is that first vertical line we're seeing in the curve here at the very bottom, the temperature begins to increase somewhere within the stratosphere. And the reason being is because of the composition of our atmosphere. So solar light is for the most part able to pass through our atmosphere with at least the light that comes from the visible portion of the spectrum, which is where solar light peaks at. A lot of that light's able to pass through our atmosphere and actually reach the surface of our Earth. Well, that light heats up our Earth, but then our Earth re-emits some of that energy. And it re-emits that energy in the form of infrared radiation. Well, within our atmosphere, we have certain chemicals, or certain, I don't want to say chemicals, but certain molecules that are really good absorbers of infrared radiation. If I'm remembering correctly, specifically oxygen, carbon monoxide, and carbon dioxide. This actually all plays a major role, what I'm talking about here, in the greenhouse effect. And so, but the key thing what I want to note here is what's happening is that we have these convective currents of essentially we have these bubbles, for lack of better words. We have these bubbles of heat, of energy, of heated gas, heated air, that become buoyant in the cooler air around it when close to the surface of the Earth. These bubbles of heated air are then able to rise higher into our atmosphere, where they'll eventually release that energy or dump that energy somewhere within our atmosphere, which in this case corresponds to a large portion of the stratosphere, which is able to actually heat that portion of our atmosphere. Which is the reason why we're seeing within that particular zone of layer of our atmosphere that the temperature rises. Eventually, though, that particular heating mechanism isn't isn't good enough to continue going to higher altitudes, and the temperature will begin to drop off again within the mesosphere. And then finally, we get to regions of the troposphere where the temperature begins to rise again. But this particular portion of the increase in temperature is primarily attributed to solar processes. But another key thing that I think is interesting is within this plot is that if you look at the far left hand side of the image, we kind of see what sort of phenomena are occurring within these different layers of our atmosphere, such as like meteorites kind of burning up within the mesosphere, and then we also have the aurora lights happening within the thermosphere, which we're going to actually come back to talking about the aurora lights in a moment. Okay. And so, of course, if I'm going to be talking about Earth's atmosphere, another key thing to talk about, of course, is its composition. And so, what I'm showing here is essentially a breakdown of the composition, which basically is the types of materials that our atmosphere is composed of. Or another way of putting it, what our air is composed of. Um, and so, on the left side of this image, we're kind of seeing a breakdown of essentially 100% of what the atmospheric composition is, where a large majority of it is nitrogen. The next largest the next substance that's largest in amount would be oxygen. Then we go on to argon, and then trace elements of other things. One thing that was actually very interesting about this particular breakdown of the atmospheric composition is the fact that the ozone is, of course, is a part of this. But at one point in Earth's history, ozone was not present. It appears to be that ozone didn't come around until we actually started having life on our planet, because ozone is made of oxygen, and we know that life, for the most part, um, there's a very interesting relationship between animals and plants, where plants produce oxygen, and essentially, I guess, they produce oxygen and they take in carbon dioxide, and animals produce carbon dioxide and take in oxygen. But yeah, the ozone didn't come around until we start having life on the planet. And we're lastly going to finish up our discussion here talking about Earth's magnetic field. Um, this particular topic is actually, to me, the most interesting because it's related to what I know most or know best. Um, but to talk more about the magnetic field, so Earth's magnetic field is produced by a dynamo process, excuse me, occurring within the Earth's interior. Essentially, what's occurring is that you have very small, let's say, pockets of magnetic field occurring within the Earth's interior, and then you have these convective currents or convection occurring as well, which in itself together produces electrical currents. And whenever you have an electrical current, electrical current itself will produce an even larger magnetic field. Now, this process will continue to increase even larger magnetic fields, and that's how we're able to get the magnetic field that we have with Earth. And one of the key things I want to note about this image that I'm showing you here on the right is that it shows two different axes, where one of the axes corresponds to our rotational axis. However, the other axis, which according to our actually it's hard for me to read what that angular separation is, but the other axis corresponds to our magnetic axis. And so as you can see that they're not perfectly aligned with one another. There is some sort of separation between the two. Did I miss a question there? And so then another key thing about our magnetic field is that it's also being used. Well, it's not being used, but it also has the ability to trap charged particles. Um, Typically, these charged particles are coming from what's known as the solar wind, which is another topic that we will be talking about in the future. But these regions in which these charged particles are trapped are known as the Van Allen belt radiation belts. And the reason why they're known as radiation belts is because these particular trapped particles are emitting light due to the synchrotron radiation process. And lastly, I'm seeing now that it's almost 1:30. Um, is Earth's magnetic field being able to protect us from solar energetic particle events, um, or just in general, also the solar wind itself. But basically, this is a nice little image showing Earth's magnetic field defending us against essentially the blasts of charged particles that are streaming, in this case, from the sun towards Earth. And that basically is the end of today's discussion. And opening up the chat for even more questions. Yeah, our magnetic field does a lot of work. I mean, it's very useful against charged particles coming from the sun. However, for charged particles that are more energetic than the particles that are being produced due to solar processes, our magnetic field isn't that powerful against. And the reason why we know is because we end up getting these other events known as um, cosmic ray air showers. Cosmic rays being charged particles that are zipping around in our universe. Hey, Larry, you said gravity helps. I was wondering, what did you mean by gravity helps? So, are magnetic fields always differently oriented than spin? Um, with all the objects that I've looked at that have magnetic fields, typically that's the case. But then again, I mean, oh, you're funny. You're funny, Joe.
Got all the jokes.
Oh yeah, in our future streams, we're definitely going to talk about the other planets within our solar system and kind of do a comparison and contrast between Earth's properties versus other planets in our solar system. Hey, Dale. Well, planetary science. And that was to answer Farrell's question about what science/discipline deals with measuring the albedo effect correctly. Um, I've heard albedo that particular concept brought up in discussions that are related to exoplanet science. Um, So, planetary science. As you can see from the equation I showed earlier, though, it's very important to understand how well the planet's able to reflect any sort of radiation that's hitting it. Let's see. Oh, if you want to measure the reflection of concrete, what type of science would it be? The interaction of light with matter. Let's see. Uh, what's coming to mind is spectroscopy, but that really deals a lot with being able to determine the composition of things. And typically, when I think of optics, I think of like mirrors and lenses. But I guess it's material science. Okay. Yeah, sorry guys. Just reading through some of the comments here. Well, guys, thank you for tuning in to today's stream. We will be back Friday with a new topic. So Hanny, what do you mean by does the sun tilt? This
I think he's that rotates on a tilted axis like Earth and most other planets.
Oh, I see. Oh, I seem to. Did I do something wrong with your? Hanny, that's a very good question. I mean, I would assume that the sun's orientation has not changed. Thanks, guys. But like I said, we'll be back on Friday after Daily Space. And so we'll see you guys then. Thanks for joining, guys. Bye.